What interesting scientific concepts are involved in the movie Interstellar? Do the stunning visual effects in the film align with real scientific principles? In the movie, the characters, including the protagonist Cooper, travel aboard the spaceship Endurance on a 2-year journey to a wormhole near Saturn. First, we know that the orbital radii of Earth and Saturn are 150 million kilometers and 1.43 billion kilometers respectively. By subtracting these, we can determine the shortest distance between them, approximately 1.3 billion kilometers. By dividing this distance by the 2-year travel time, we can calculate the spacecraft's speed to be about 70,000 kilometers per hour. The fastest known manned spacecraft to date is Apollo 10, which reached a top speed of around 40,000 kilometers per hour, making the speed depicted in the movie attainable for future human missions. The spacecraft's design incorporates a revolving ring architecture, facilitating the acclimation of Cooper and his companions to living in space. This rotation uses centrifugal force to simulate gravity, similar to that on Earth. Using the centrifugal acceleration formula, we find that it takes 5.7 seconds for the ship to complete half a rotation and 11.4 seconds for a full rotation to achieve a gravitational acceleration of 9.8 meters per second squared. This implies that the radius of the ring is about 13 meters, or a diameter of approximately 60 meters. For comparison, the International Space Station's width is around 70 meters. When the Endurance finally reaches the wormhole after 2 years, they see what appears to be a giant, transparent crystal ball in front of them. A wormhole, as derived from the theory of general relativity, is a theoretical astronomical object that can link 2 distant regions of space. Not only can the spaceship pass through this tunnel, but light can also traverse it, allowing us to see the other side of the universe from one end of the wormhole. To verify the wormhole visuals in the film, we simulated a similar wormhole model. We smoothed the edges for a better transition effect and placed a camera on one side. Using 2 images to represent the 2 sides of the wormhole, this camera can simultaneously capture light from both spaces. The trajectory of light moving in distorted spacetime, along with the color of light received by each pixel, will ultimately result in a wormhole image in the simulation program. At this point, we can find that it is astonishingly similar to the wormhole effects in movies. However, when we traverse the wormhole from the camera's perspective, we find that it is completely different from the special effects in movies. This might be Director Nolan's way of allowing the audience to better experience the visual shock of traversing a wormhole. When the spaceship passes through the wormhole and comes to a supermassive black hole called Gargantua, there is a planet next to this black hole known as Miller, which is the destination of this journey. The surface of this planet is entirely covered by seawater, and due to its proximity to the strong gravity of the black hole, it has very extreme tidal phenomena. Colossal waves reaching a height of 1 kilometer occur on its surface. Simultaneously, gravitational time dilation means an hour spent on Miller's planet is equal to 7 Earth years. Are these wonders consistent with scientific principles? Essentially, the towering waves result from tidal forces emerging from the interplay between the gravity of the black hole and the centrifugal force due to the planet's trajectory. Newtonian mechanics explain this. By evaluating the mean tidal force, this influence can push water from regions of low to high tide. During this conversion, the water is acted upon by the tidal force, with the performed work being equal to the product of this force and the displacement, the planet's radius. Inserting the earlier computed mean tidal force into the equation, where work equals the gravitational potential energy, allows for the determination of the requisite distance between Miller's planet and the black hole for the creation of kilometer-high waves. If the planet Miller is similar to Earth, and considering the film's setting where the black hole's mass is 100 million times that of the Sun, we can calculate that Miller's planet is about 45 billion kilometers from the black hole. Additionally, knowing the mass of the black hole, we can use the formula for the Schwarzschild radius of a black hole to derive that the radius of Gargantua black hole is approximately 300 million kilometers. If we compare this distance with the images in the film, we can find that the scale of this black hole is very close to what Gargantua looks like from Miller's planet. Now let's take a look at the time dilation issue on Miller's planet. According to the movie's setting, 1 hour on Miller's planet is equivalent to 7 years on Earth. Doing a simple calculation, we can conclude time on the entertainment planet passes 60,000 times slower than on Earth. For a static black hole, when we input the distance into the mathematical expression for time dilation, we find that time on Miller's planet slows down by only 1.5 times, which is far from what the movie depicts. For time to dilate by 60,000 times, Miller's planet would need to be located exactly on the black hole's photon sphere, but at this position, only photons can orbit the black hole stably. This means that a stable orbiting planet cannot exist in that region. However, these calculations only apply to a non-rotating black hole, whereas black holes can actually spin. The faster a black hole spins, the more likely it is to have stable orbits near its boundary. For a planet to experience 60,000 times time dilation compared to Earth, it would need to be just 6,000 kilometers from the black hole's boundary, with the black hole spinning at nearly the speed of light, which is clearly not as depicted in the movie. Additionally, the exaggerated visual effects of the black hole in the film are also controversial. To simulate a realistic black hole's appearance, we used ray tracing technology and the geodesic equations from general relativity to create such an image of a black hole. You can see that the light around the black hole is distorted due to Einstein's gravitational lensing effect, which is not shown in the film. There is also an accretion disk near the black hole, where the gravitational pull of the black hole distorts the surrounding matter, and even light. The rotation speed of the accretion disk can nearly reach the speed of light, causing friction that increases its temperature to billions of degrees Celsius and releases a lot of radiation, posing fatal harm to spaceships and humans. The high rotation speed causes the disk to emit a blue glow due to the high energy. In the movie, however, the accretion disk's temperature and pressure are greatly reduced. The rapid rotation of the accretion disk also makes one side of the disk appear brighter than the other. This is known as the Doppler effect, which is also not shown in the movie. If these missing phenomena from the film were considered, we would get a representation of interstellar travel that is closer to real physics.